Hello, everybody. My name's Gavin Bierman, and I work in the Java Platform Group in Oracle. I'm actually based in the UK, in Cambridge, so it's great to have a Java meeting in my own country. And thanks very much for coming. I know you're all very busy, so really appreciate it that you've taken time out of your day to come here. So the aim of this talk is to give you a picture of some of the directions that we're taking the Java programming language. And as we have a new JDK launching any day now, I'm going to show you how some of the new features in that JDK and in more recent ones really are hopefully going to help to turbocharge your developer experience. I want to try and give you some insight into some of the motivations behind those features and how they unlock a new style of programming for Java. And if I don't run out of time, I'll try and wrap up by showing you some features that are going to appear in some future JDKs. So let's get started. I need to remind you that I'm only showing you some of the new features that are going into the Java language. As you hopefully heard in the keynote, there are many other exciting projects, Valhalla, Panama, Leiden, Loom, and many others. And there are talks about those elsewhere in today's meeting. So I think it's fair to say that Java remains a very vibrant product. But my talk is about Project Amber, which is an umbrella project that covers new features and extensions to the programming language itself. So it's important to know what the goal of Project Amber is. If you go to our webpage, you'll read that it says that the goal of Project Amber is to explore and incubate smaller productivity-oriented Java language features. Now, Project Amber has been pretty prolific so far in bringing new features to language. So if you look at the past 10 JDKs, you'll see that we've been delivering quite a lot. And we've been taking advantage of this 6-monthly release cadence that George spoke about in the keynote by previewing features before we deem to set them final and set in stone for the rest of time. Preview features ship in the GA release, and they're specified in the standard, but they're disabled by default, so there's no risk of anyone using them by accident. So as an example, if you look at the first row of this table, you'll see that we previewed switch expressions in Java 12. We previewed them in Java 13 with some small changes based on feedback from the community and our expert users. And then we standardized them as a final feature in Java 14. And this has been a very successful strategy so far for us on Project Amber. A preview feature release is still a high quality release with a full featured implementation, full test suite, and a full specification. But we use the preview period to gain experience ourselves, as well as feedback from our partners and the broader community to assess the design. And then at the end of the 6-month period, we can decide to either preview again to get some more experience, we might make some amendments and preview again, we might propose to finalize it, or we might drop it altogether if we decide it was a bad idea. So far, we haven't come up with any of those in Project Amber. And as you can see with JDK 22, very shortly, it's another great release. We're finalizing a really useful pattern matching feature. We're re-previewing two other features, and we're previewing one for the first time. So another good release for Project Amber. I just want to reflect a little on the mission statement and that phrase, productivity-oriented. Unfortunately, what most people think about when they hear about Project Amber is wrong. They think it's about syntax, or it's about removing boilerplate, or it's just about tiny little language features that barely move the needle. What we're actually interested in is language features that expose programmer intent that at the moment is somewhat hidden in the language, maybe even leading to new ways to write Java code. After all, the problems that Java developers are having to solve today are very different from the ones that they were facing in 1995. And of course, we take very, very, very seriously the issue of compatibility. in all the ways that compatibility is supported in the Java platform. We really don't want to break anything. So let's get to the meat of the talk. I'm going to talk quite quickly through some of the features that we've shipped already in Project Amber, and then try and show you after that how they come together to offer you new ways to think about and to write your code. So the first feature I'm going to describe is records. These were finalized in JDK 16 and proposed by JEP 395. So at the top of the screen here in green, there's a record declaration. So a record is a Java class, but it's a special sort of class, and it models a nominal tuple. Now, nominal, because every record class has a name, it's a Java class after all Java classes have names. And it's the tuple is the thing between the brackets, right? These are known as components in JLS speak. And this is in the entire declaration of a record to represent a two-dimensional point. The compiler will do the rest of the work for you. And again, the thing here is the programmer intent, right? The programmer wants to say every point is a pair of integers exactly, that's it. And the great thing about record classes is that's essentially all you have to say. Records are classes, so we make new values using new as normal. And indeed, the thing to notice here is that the compiler wrote the obvious constructor for you. In this case, for this record, the constructor takes two integers and assigns the x and y backing fields to the two integers that you pass in. So we call this constructor the canonical constructor. And again, the compiler writes it for you. It just looks at the record declaration and figures out what to do. Of course, if you want to write your own constructor, no problem, just write it. So the canonical constructor, as I said, takes in those values for the x and y components. There's obviously no constructor that takes a single integer. If you wanted one of those, you'd have to write it yourself. So the constructor that the compiler writes for you is driven entirely by the signature that you see in the record declaration. The compiler auto-generates getter methods for those components, and we call those accessor methods. And they have the same name as the components themselves. And the fields that actually back up the values of the instance are actually private. So you have to use the accessors to get at the components. Records are immutable. So once you've made one, it's done, it's set in stone. You can't change any of the component values. So if you remember all your university lectures about the great advantages of functional programming and using immutable data structures, here you are. You get them too now if you stick with your records. And as you would expect, the compiler auto-generates implementations of the object methods. So records come with an equals method that compares values using only the components, and it also comes with implementations of the hashcode method and the toString method. It's all written for you, you don't need to do anything. Of course, if you want to override them, do your own thing, you're free to. And just in case you were wondering, can we write generic records? Of course you can, they're classes. So whilst it might look like boilerplate reduction, it's just about taking verbose class declarations, making them smaller, it really isn't, okay? The point here is about programmer intent. So records have an important semantics, right? Informally, as we say, they're about the data, the whole data, and nothing but the data. So in other words, the component list, that tuple, the thing between the brackets, that's all the data in a record. There's no secret private components, there's no subtyping. If you have a record, you know everything about its contents. So records completely expose all their state. Now what you get from that is an important contract, and I put it here in green, sort of as an equation, right? So if you get a record value, you extract all its component values, and you build another record with those component values, that resulting record value is equal to the one you started with, always. And that's a really important semantics. That's actually at the heart of why functional programming using immutable data structures is a powerful thing. And you get that same contract here. Another cool thing about records, as I mentioned, is that they have this guaranteed canonical constructor, right? Every record has one, either auto-generated by the compiler, or you could write one yourself. So, for example, if you wanted to impose your own domain-specific constraints on the record, so say you only want to allow, I don't know, integer values greater than 13 or something in your points, you could impose that, and it means that you can never construct a record that breaks that domain-specific constraint. So deserializing record values, we actually build on this for the libraries dealing with deserialization. So when you deserialize a record value, it always uses the canonical constructor, which means that if you had any domain-specific constraints, all the values you get are guaranteed to satisfy that. So this is actually an example of why using records is better than using standard classes. Okay, let's look at another feature, and that's sealed classes. These finalized in JDK 17, and they were proposed by JET 409. Now, sealed classes address a long-time limitation in the Java language. Until sealed classes, you had only two start choices when declaring a class or interface. You could either let anybody extend you, or no one was allowed to extend you by declaring your class as final. So, for example, we may want to declare an interface shape, but we might want to say there are only two implementations, circle and rectangle. Now, previously, there was no way for you to declare that intent. So you always had to program defensively and maybe say, well, there might be other things. So every time I take a circle, I better check whether, take a shape. I obviously do the right thing for circle and rectangle. Oh, I better check that it's not some other crazy thing that's been programmed by somebody else. With sealed classes now, there's a mechanism for you to say precisely what you want, which is, I only want to permit two implementations, and we have a permits clause now that where you state precisely the permitted subclasses. If you then go and declare a subclass, or anyone else tries to declare a subclass that's not on that permitted list, it's actually a compile time error. So every subtype of a sealed class has a constraint, which is it has to itself say whether it's sealed or whether it's final, or you can say, oh no, I'm an open guy, I don't care who extends me, in which case you actually have to say that explicitly, and we introduced a hyphenated keyword, the first one in Java, which is non-sealed. So every subtype of a sealed type has to be either explicitly sealed, final, or non-sealed. So this is very cool. We now have a way for programmers to express directly something that's hitherto just been part of the semantic model, but now it's part of the code itself. The reason, so what's the point? Well, because often when declaring hierarchies, we want to model this fact that an X is either an A or a B, but nothing else. This is often useful in libraries where you want to write an abstract interface for users, but you want to provide the implementations, right? But before it was very hard to do that because if it was open, it was hard to constrain. You'd have to resort to some sort of coding tricks or something to do that. Another thing we might hope for is that this programmer intent, an X is either an A or a B, might be used by other language constructs. And indeed, we'll see a little bit later in the talk that this is actually the case. So we can actually build on this fact to make other language constructs a bit more pleasant. So let's move on to another feature that we shipped, which is pattern matching. which was proposed by JEP 394. So pattern matching itself is a whole subject, and I've given talks on it. You can check them out. And at its heart, though, is a programming idiom that all Java programmers are actually familiar with. So let's look at this code here in the green box. We have an object which we think is a string. So we test it using an instance of to see if it is a string. And if it is a string, well, we'd like to get the string value, please. So we use a cast to do that. And notice that this is obviously a conditional process, right? We use an if. And in the then block, we can use the result of that cast. So we can actually use the string that we were after all. So this test and if true, extract the value idiom is very common in Java code. I'm sure you've seen it many, many times. But it's a bit laborious because you have to mention the type many times, which is a pain. But more concerning is that, of course, the compiler doesn't know that this is your intent, right? It's just code. So it doesn't check, for example, that you use the same type. You see here we have string appearing 3 times. But it doesn't check that. It just checks that each statement's OK. It doesn't know that what you're doing is testing and extracting. So this is an example of sort of semantic intent that you have in your mind as a developer, but the compiler has no way of knowing that that's really what you're doing here. So it isn't able to enforce that atomically. It just sees code, so it doesn't know. And this is what pattern matching does for us, is it enables us to make that semantic intent clear to the compiler so it can check the code for us. So here's a type pattern, and it's the simplest form of a pattern. So what's a pattern? Well, a pattern really is just a test. In this case, the test is whether a value is an instance of a string, but we'll see other sorts of patterns in a little while. Passing the test is called matching, right? So it's pattern matching. A pattern can also declare variables, and if a value matches a pattern, then these variables will always get initialized. So in our example here, if x is a string, then s will be initialized with the string value, okay? And then in the then block, the string s will be in scope. So again, the semantic intent here, is it a string? And if so, let me have the string because I want to do something with it. It's now part of the semantics of the construct. You don't have to write the cast. You don't have to write that assignment. It's all there in the semantics of pattern matching. But moreover, the fact that they were disconnected before and maybe you got them slightly out of alignment is all now impossible. It's all generated for you by the compiler. So this code is not just better because I think it's more readable, but also it eliminates a place where bugs might hide, and getting rid of bugs is good. So. It's not just instance of. In the previous example, we use instance of with a pattern. Other constructs can be made pattern matching aware as well. So in JEP 441, we proposed adding pattern matching to switch. And this was finalized in JDK 21. So we've extended the switch so you can use patterns in your case labels. So we see here, we've got a couple of type patterns as labels. Now, the semantics of switch is what you would expect, right? So to see if a pattern case clause applies, we just see if the pattern matches. Now, the cool thing is that if the pattern does match, then the variables that are declared in the pattern are available for you to use on the other side of the clause. So in this first case here, you can use the variable c, and it will be the circle. Now, we made one important design decision when extending switch in this way. In fact, earlier, when we designed switch expressions, which is an earlier feature in Project Amber, we introduced the idea of an exhaustive switch. So clearly with switch statements, it's possible that no case label might apply, in which case the statement just evaporates and we get on to the next statement, right? But clearly when we were designing switch expressions, you expect every expression to have a value. So we didn't want to allow you to write a switch expression where none of the case labels would apply, because then what would be the value of the switch expression? Surely not null, right? Or something horrible. So we introduced the idea that for switch expressions, the block had to satisfy an extra condition, which was that it had to be exhaustive. In other words, the compiler would check all the labels and make sure that there was a label for every eventuality, right? So there wasn't some missing label. So often this just means that you need to put a default, okay? Now we got a lot of feedback with that feature saying, oh, I love that, I love that. Please do that for switch statements. I want the compiler to check that everywhere. Now, clearly we couldn't make that change because that would break the entire world's code base. But we realized that when we extended switch to support patterns, we could do something. So what we've done here, or what we did with pattern-enhanced switch, is that if your switch statement has a pattern as any of its labels, then it has to be exhaustive, okay? So this kind of is the new style of switch programming. So if you use a pattern, you have to be exhaustive. But that's very cool because now the compiler checks your switches for you. And as I hinted at a little earlier, we can be a little bit clever. In this example here, we're switching over a shape. Remember, a shape is either a circle or rectangle and nothing else. In our switch here, we have a case for the circle, and we have a case for a rectangle. What other things could a shape be? Nothing. So this switch is exhaustive, right? You don't need to write default. It knows there are only two possibilities, so this switch is exhaustive. The cool thing, another cool thing, is if you forgot one of those, like you forgot the circle case, obviously it's a compile time error. So the compiler checks for you to make sure that you've included all the cases, which is very nice. So type patterns, as I mentioned, are only just one kind of pattern, the simplest kind. In JET 440 that we finalized in JDK 21, we introduced a new form of pattern called the record pattern. So let's imagine that we've got this record class declaration here, a circle which takes a point, so another record, a center, and an integer valued radius. And now we have a new form of pattern called the record pattern, and this combines both a type test and extracting the component values. So in this code here, the shape value matches this record pattern circle, point, center, int, radius if, firstly, it's an instance of the circle class, and then secondly, if it is, then the variable center will be initialized with the value of the center component, and the radius variable will be initialized with the value of the radius component. So this is quite a lot of semantic intent, right? Because you're saying, is it this type? And also, can you grab all the values out and assign them to these variables? But you just declare it. You don't have to write any of that code. Compiler generates the code for you. Compilers are good at that sort of thing. We just write the declarative intent that we want. We want this thing to be a circle containing these two values, and please assign them to these variables so I can use them in the then block. You'll be pleased to hear that record patterns support the var type inference feature that you'll be familiar with for variable declarations. So if you don't want to write the type for the component, for the pattern variables inside that pattern, you don't need to, you can just write var. The compiler will figure out what the types of those variables are. Now, we're used to being able to nest class declarations, and obviously we can nest record declarations as well. Here, the record class point is nested inside the circle record class. This obviously means that when we build a value, we'll have nested new expressions, and you can probably see where I'm going. If we want to pull them apart, then we can freely nest our record patterns. So in other words, pattern matching is kind of recursive in this case. So to match this pattern here in the green box, the value must be a circle, and then its center component must recursively match the record pattern point var cx, var cy. Now, obviously, either the whole pattern matches or it doesn't, right? There's no concept of like, oh, I match partially, right? So when you say, is it an instance of this pattern, either all the patterns succeeded everywhere or it didn't, okay? Sometimes when using a record pattern, we don't care about some of the components, right? And we have another pattern written using an underscore to say that we don't care. Whatever the component is, it matches, okay? So in this example here, we're checking whether it's an instance of a circle, and we want to get the point components out, but we don't care about the radius. So you just write underscore. Again, just makes it a little bit more succinct. Okay, so far I've shown you a number of Amber features, record, seal classes, pattern matching, enhanced switch, so on. But there's actually a secret agenda here. So these are not just features, they're not features in isolation. They're actually combined to enable developers to tackle problems in an entirely new way. So afraid I can't hide my sort of academic past. I'm going to give you a lecture about what's going on in our minds. So why are we doing this? So let's go back to the beginning, right? So we're all Java programmers. So we all like object-oriented programming, right? And object-oriented programming, like all paradigms, aims to manage complexity. That's what we're dealing with. And this complexity comes in many forms, and not all paradigms handle all forms of complexity equally well. That's why we're looking at other paradigms to get inspiration. And as the name suggests, object-oriented programming tries to model, or encourages us to model complex entities and processes using objects which combine state and behavior. And this encourages encapsulation, so where behavior mediates access to the state, and polymorphism, where multiple kinds of entities can be interacted with using a common interface, right? This is what you're all taught. And object-oriented programming has been incredibly successful, is great, is particularly great at defining and defending boundaries. We have lots of boundaries in our software system. So there's maintenance boundaries, compilation boundaries, so on and so forth, versioning, lots of boundaries. And languages OO languages like Java gives lots of tools for precisely defining, navigating, defending these boundaries. And in fact, they're so good at it, we often forget that that's what they're doing. And dividing a large program into smaller bits with clear boundaries helps us manage the complexity because it enables us to use modular reasoning, right? The ability to think about things in isolation. But things have changed, right? So Java was invented in the era of the monolithic application, and it's a fantastic tool for building apps like that. But as I say, things have changed. Not all large applications are architected in the same way anymore. Lots of large applications now are composed out of many smaller services, and those services look quite different, right? One aspect of these services is that they exchange data, not objects, not big, heavy objects, which means that the strengths of object-oriented languages, which is managing complexity and boundaries and so on, is kind of less important. And what's more important is exchanging this pure data between the services. So what we take from this is really that Java kind of needs to be a little bit more agile at handling pure data. And what do we mean by that? Well, what we mean is kind of modeling data as data, right? Data is immutable, data's typed, of course. With Java, we're not giving up on types. It's a good idea. Don't be tempted with other languages that don't think that. Data is consistent, so preferably we'd prefer it so you couldn't actually represent invalid states. Validity ought to be a test when constructing the data. We need to be able to convert data to or from the wire format, but we don't really, come on, we don't want to program in JSON, right? So we'd expect whatever representation we have to be a bit more Java-like, so some sort of Java-type JSON thing. And we don't want data, as is commonly the case, to be just represented by strings, which is the lowest common denominator in many applications. This is what one might refer to as, instead of strongly typed programming, it's like stringly typed programming, right? And we all know how painful that world is. So in other words, Java's approach of sort of class-based modeling and strong typing still tremendously important, but for smaller programs, but just in different ways. So, and I want to make it clear, I'm not like dissing Java or object-oriented programming here. I'm just saying that in many cases, we want to really use classes to model data rather than these big business entities and processes. So to make this a little bit more concrete, less abstract, I'm going to walk you through an example. So it's an example of taking a problem and kind of looking at it in a sort of data-oriented view. And when you kind of look at it afresh and you use the great new features of Amber that I've just showed you, you'll see that there's kind of new ways to write your code, which I think is kind of exciting. Okay. So here's the example, right? So it concerns a type future that we actually introduced in Java 5. So future is a computation that may run concurrently with its initiator. And the computation represented with a future may have not yet been started. It may have started but not yet completed. It may have completed successfully, or it might have completed with an exception, or it might have timed out, or it might have been cancelled by an interruption. So if you look at the get method for future in the Java API, you kind of see these possibilities, right? You see that the get can return new values, or it might throw some exceptions. So if the computation is not yet finished, the get method blocks until one of the completion modes occurs. If it's successful, it returns the result. If computation completed by throwing an exception, then we wrap the exception in an execution exception and give that back to you. If computation timed out or was interrupted, we give you a different sort of exception. So once I've given you this explanation, sorry, I know it was a bit fast, but you kind of look at that code and go, yeah, all right, I see what's going on here. Okay, but that API is kind of precise. I mean, it kind of says what's going on, but it's actually a little bit painful to use, right? Because the problem is that there's multiple control paths here. So there's the normal path where the call to the get method returns a value, and then there's a whole bunch of failure paths, each of which you have to handle in a separate catch block. And the real problem here is that we don't get a lot of help from the compiler about that semantic intent, about what's a future, what can happen when you get call get. You kind of don't get a lot of help about the support for coding that bigger semantic problem. You just get these constructs and you have to deal with it yourself. So let's look again at the problem, but let's think about data, right? So what is it we want to model? So let's just make a slight change. So let's just say the get method always returns a value, right? Data, value. Always get a value back from the get method. Okay, so what can this value be? Well, could either be something modeling success, could be something modeling failure, could be something modeling timeout, could be something modeling an interrupt, okay? So, all right, let's run with this idea. So let's say, let's rewrite the get method to return a value. Let's call this type async return. Okay, so this is the data-oriented, data. Okay, so, well, I just said that data could be one of four things, right? So let's model the success thing using a record. Records are great. Records are good for modeling data. So It's a record class success with a record component containing the return value. Excellent. Let's model failure using another record class that's got a throwable component. Okay, perfect. Let's model the timeout using a record class called timeout. Hasn't got any components. It's okay, still data. Let's model the possibility of an interrupt using a record class interrupted. Again, no components, still data. That's good. And those are the only possible ones, right? I said there's one of four things. So let's make a sealed interface. Let's make async return a sealed interface with those four permitted subtypes. Records are always final, so you don't have to say final record. Records are always final. Now, the nice thing here is that this wonderful declaration matches perfectly the design intuition, right? There are four, we've got a value, it could be one of four things. Here are the four things, nothing else. Perfect. But the real win is kind of our client experience of using this version of a return type. So we'll invoke the get method to get a value, and then we want to examine it, right? Well, how do you examine values in this sealed hierarchy of things? Hey, let's use switch. I just told you I made switch better. So let's go with a switch. What are the implementations of async return? Well, it could be a success. So let's use a record pattern to match that value, okay? Or it could be a failure. Let's use a record pattern to match that one. Or it could be a timeout. Again, another record pattern to match that possibility. Or it could be an interrupted value. And again, we use a record pattern to match that. And that's it, right? So the four possible sort of data types of async return, which are modeled using record classes, can be matched with a switch with four clauses, each one using a record pattern to match and pull apart the values, so you can use the components on the other side of the switch clauses. So this is a much simpler control flow. Each case is defined more precisely, and we don't need to worry about like accessing values that are not initialized. We've all played with APIs like that, right, where you've got a get foo, but then you've also got another method which says, is foo really there? And you're supposed to call that before you get the value, and there's nothing to stop you doing the wrong thing. Now that's all gone away. It's all dealt with by the data type itself and by the compiler checks. Again, if I'd forgotten any one of these four cases, the compiler would have told me that I'd forgotten. And those are the only four that you need, so you don't need to write a default and so on. So this is much more lightweight style of programming, right? No deep class hierarchies, no visitor patterns, just program directly with the data. So, okay, so I've looked at some recent features of Amber and how they lead to this sort of slightly more data-oriented focus style of programming in Java. So let me wrap up by looking at a feature that's shipping in JDK 22 next week. And then I'll also, if I don't run out of time, look at a feature that we're proposing for JDK 23. Okay. So this one will go faster because George spoke about it. I didn't realize. But anyway, I'm going to shift gears slightly. You've perhaps all seen this example. Roll back the years. Let's look at our first program that we wrote in Java, Hello World. Okay. We all see this and go, oh gosh, this is so painful. There's so much stuff in here. And the problem is that none of these concepts really are necessary to understand how to write this program, right? You don't really need to know about the difference between static and instance to write Hello World, or you shouldn't. So all this kind of noise is why people think Java's hard, but Java really isn't hard. It's just that if you take everything about Java all at once, yeah, sure, it's a big language, right? But all languages like that. But this has a sort of pernicious effect, which is it makes teaching Java sort of unnecessarily complicated, right? So you have to, as teacher, which I once was, you have to tell programmers, you know, your beginning students, you have to say, yeah, you have to write this stuff. Don't worry about that. Don't worry about that. Don't worry about that. And this is slightly unnerving as a beginner programmer. It's like, well, if I didn't have to worry about it, why do you tell me about it? So we want to make it easier. We want to make Java easier. So we want to reduce this initial complexity for beginner programmers. So we can look at sort of trimming some of this additional complexity. So, command line arguments is a lot of complexity. I don't think many beginner programmers worry about that for several weeks. So, it would be great if we could just remove that from their attention. And then we'd also have the nice advantage, don't tell them what an array is, and the fact that array is indexed from 0, which blows their minds, and so on. Accessibility is very important, but it's really useful for when you're building big systems. And this is a one-line program. It's not a big system, and it's not going to be private, is it? It's always public. Everything's public. So why do we even have to say it? Static's a lot of noise. Surely no beginner needs to know about static methods. They just want to write some methods and try them out. Requiring beginners to know there's a system class with from an auto-imported package that has a static field. That field's got a type print stream, and that's where all the overloaded print methods are for the console. Like, oh, come on, let's relax a bit. And once we start looking at it, why do we even require the beginners to write a class? They're not going to build an instance of this, right? They just want to run the method. And it's undoubtedly in a file called helloworld.java. So if you need to give it a class name, why not just call it hello world? Why doesn't the compiler just call it hello world, right? So really what the beginner wants to end up with is something like this. So the great thing about this is it's much simpler for a user to begin with. And then as they want to slowly understand things, then they can add them to the program, right? So let's say they've written this and it works, it's like, fine, okay, they want to pass in a console argument, sure, they just add it, and that works. They want to make the main method static, sure, do that, it still works. So slowly start up from simple and get more complicated. That's how you learn things, right? You don't start from the most complicated thing and work down. So in JEP 445, we took the first steps in doing that. So you can actually do this. You can write hello world as a one method thing. We didn't quite get rid of the print line, the system.out thing, but we'll get there in the next one. And you can just launch this program from the command line. And again, it might look like syntax and boilerplate, but it's kind of more subtle than that. It's about making the simple programs be simple. And also if you look at a lot of the comments on Reddit and so on, don't ever do that, but if you do, you'll see everyone goes, why can't you ban this and ban that? But then you'd be defining like a beginner's dialect of Java. We absolutely 100% don't want to do that. We want this sort of thing to be real Java, right? So you just slowly add new things, you still Java, it's all Java, right? There's no dialect, it's just Java, it's just tweaking how the launcher works and so on, but it's all Java. And again, as George mentioned, there's a very nice sort of meditation on this by Brian Getz. There's a paper called Paving the On-Ramp. It's a very good read. Okay, so JDK 23, records are immutable, right? So if you want to create a new value from an old one, well, you do everything by copying, right? It's functional programming. In other words, we don't mutate you don't take a record value and mutate a component. You can't, it's immutable. So you have to take an old one and create a new one. So let's imagine we've got a point, now points are three-dimensional. And we take a point and we want to get a new one. So now we have to remember the canonical constructor takes an argument for every component. So now we need to copy all the components over and build a new one. Oh, that's a bit ugly. Can't we do better? Oh, well, we already knew the answer to this, right? We're all object-oriented programmers. Wither methods, they're great. So let's write those for the record. So that's good, because now here I want to write a new point, and it copies the y and the z value, and I don't need to mention them, right? The wither does it for me. That's great. With the withers, I can chain them. That's great. Okay, that's good. But, what if I want to do two at once? Oh, rubbish. Okay. Or maybe I write withers that take two of them. Oh, okay. Yeah, what if I've got 26 components? Oh, God. And now I'm writing tons of withers, right? I thought all records were supposed to be this sort of great compact thing. So it's not going to work, right? So let's do something better. So we are going to do something better. A new expression form, which you might call with expression. On the left-hand side is a source record value. On the right-hand side is a block. Implicitly, at the start of the block, we copy all the component values into variables with the same name as the component value. And then in the block, you can do whatever you like with those values. You can ignore them, you can say nothing about them, or you can start changing them. So here we double the value of X. And then implicitly, the end of the with expression, we create a new record using the values of those variables. So the ones that you didn't touch are copied, and the ones that you changed, obviously, we put those in. Great. So you can do things like calculate values for all the new components, or just two of them, no problem. It all just works as you expect. No exponential blow-up or wither methods, no wither methods at all. Just write a with expression. All this implicit variable stuff is all done for you by the compiler. Don't worry about it. Again, programmer intent. I just want a copy of this record with X doubled. That's all I want. So compiler does all the other code, writes all the other code for you. No place for bugs to hide. And of course, we can nest them too. I'm running out of time. So we have other things in the pipeline. In fact, we have loads of things in the pipeline. More flexible constructor bodies, primitive types in patterns. We're going to add things that look like record patterns, but for any old class. Very hard, but very cool. Constants in patterns, all sorts of stuff. So I hope I've impressed upon you that we're bringing lots of new features to make you more productive. We have some themes around data modeling, pattern matching, making the beginner programming experience better string handling. I haven't had a chance to talk about that, but we have multi-line strings and string templates coming through. We're evolving fast. We're evolving the open. Java's an open project. Please read the emails, read the JEPs. Please, please, please don't send us emails saying, I wish you could do this, but this symbol instead of this symbol. Or have you thought about what Kotlin? Yeah, we've thought of all those things. The thing we haven't thought about is your code base. So take one of these things, try it on your code base, tell us how it went. Tell us if it worked really well, tell us if it sucked, right? That's the stuff we don't know. We don't know how it works for your code. We have thought about every syntactic option possibility. We think of all of that stuff, okay? So please get involved, send us your feedback. And with that, thank you very much. Okay, we might have time for questions if there are any questions. Yeah, okay.
I know that pattern matching is supposed to be more on data, but is it protecting against the null?
Against null?
Against the null values.
Yes, so it does. So if you're null, it just says no, you don't match. So that's it. It's slightly more complicated. I don't want to go into it right now. So if you said, is null an instance of circle? It just says no. So if you use instance of, it just return false.
You don't have to specify it in the switch statement, for example?
No. So what we've done there is if it's null, if you switch over a null, it's an exception just like it was before. However, of course, you don't want that, right? You want to say case null, right? And you can. So we added that. So you can say case null. So if you don't say case null and you switch over a null, it's an exception just like before. That's what our fathers gave us in the language. So we stick with that. But you can write case null, in which case we say, oh, he already knew what to do for case null. And it's not an exception, then you follow that label. Thank you. Yeah. Okay. There'll be time for one more. Nope. Oh, yeah, there's one at the front. I think there's a microphone coming, sorry. I forgot about the streaming people. Yeah.
The new hello world in Java, we don't need to put imports.
No.
It's not necessary.
No. You still, it depends which version, because I've got so many versions of this feature in my head. In the version that you'll get in a couple of days' time, no, it imports as a normal class does, right? So you still have to write system.out because that's not imported to you. We hope to get around that some way. There's still some controversy about exactly what we do. We're still discussing about whether we should import more for those beginner-like things so files that just contain methods. Maybe they should import more to be more helpful. We're still discussing that. But yeah.
Thank you.
Okay. But of course, you can write any import you like, right? I mean, that's free to do. So you can write imports, methods, just as normal. Yeah. So, okay, thank you very much, everybody. Thank you.